Welcome to Array Diagnostica Pharma News. We are visiting the Norwegian University of Science and Technology here in Trondheim. We're going to visit the research scientist and inventor Catherine Taylor Norgård at the Biopolymer Laboratory. Professor Kurt Draget, Catherine and the research team has developed a compound that has remarkable effect on the mucous barrier. Hi Catherine.
Hi Thomas.
Thank you for this opportunity to hear more about your research. What I understood from talking to you, you are working with a new compound that sort of changed the property of mucin.
Yeah, that's right.
Mucus.
We are very interested in the properties of mucus and the way that mucus works. Now, if you think about it, we all have some kind of relationship with mucus. You've had a cold, you've blown your nose, but mucus is far more than that. It's a very well preserved secretion, right from corals and mollusks to mammals like us humans, and it's a secretion that's absolutely necessary. We wouldn't be able to breathe without it. We wouldn't be able to digest food without it. We wouldn't reproduce without it. Its functions are really central to life. But there are times that we want to modify or control those functions. And currently we're thinking very much about drug delivery. We're thinking about drug delivery at mucosal surfaces like the GI tract and the lungs, the respiratory tract, and the nose. And here, these surfaces, these internal surfaces of the body that are exposed to the external environment, they're covered by a protective layer of mucus. And this, we can sort of think of it as a sticky net, this gel-like material that acts as a barrier to drugs that we might want to deliver. And so what we're trying to do is modify that barrier to open a window and allow these medicines through.
So mucus seems to be sort of a generic thing that works the same way from mollusks to humans?
Yeah, basically you have a family of molecules and they work by forming these sticky gels. And those gels can be used in a mucociliary transport system to keep your lungs clean and to remove inhaled particles. They can be used to protect your stomach from autodigestion, or they can be used by a snail to transport itself along.
And your new compound, G-Block, how does it work?
Well, it works by modifying some of the properties of this net. So we can sort of say that it makes the net have bigger holes and that the net is less sticky.
So sort of slime is like loosened up or swelling up?
Yeah,
or?
To a degree. And so we then enable things that previously would have got stuck in this sticky net to get through. And here we're interested in drugs, in getting a medicine into the body across one of these mucosal surfaces.
Okay. Which type of drugs do you imagine would benefit from
Well,
this?
obviously, if we're talking about the digestive system and swallowing medicines, it's something we all do. When we're sick, we maybe take a paracetamol, we have a headache, and mucus isn't a problem. And, and for these small organic compounds, it isn't. The holes in the net aren't so small. So these traditional type of drugs, they go through mucus without any huge problems. But when we start looking at some of our newer type of medicines, our biologicals, large molecules, things that need protection, things that are packed in a nanocapsule of some form, suddenly we're in a size range that mucus can become a real problem. Because this is something that's evolved to protect these mucosal surfaces from foreign matter. And suddenly these nanomedicines look precisely like that kind of foreign matter they want to protect against.
Okay. And which type of drugs? Is it like all type? Is it like only new developments, or do you think it would work with the existing drugs as well?
Anything that is large has the potential to get stuck in mucus. And the thing about G-blocks is it doesn't require that you modify your drug in any way.
Okay.
There are stealth technologies that exist where you can, for example, pegylate the surface of a nanoparticle that will enable it to move better through mucus. But G-block doesn't require that you modify your particle. So in that way, it's something that should be broadly applicable. If you want to get your large entity, your nanomedicine, through a mucus layer, whether it be in the GI tract or whether it be in the lungs, the nose, the vagina, then you have a material that can help you, that can help to open up that barrier and let your medicine through.
So you imagine that existing medicine would sort of move easier through the barrier. You will have more medicine inside the cells.
Yeah, this is the thing, that especially when we're looking at these biologicals, they're extremely expensive. Nanomedicines, the amount of work to actually produce these are expensive materials. You don't want to lose a large proportion of your material because it's stuck in mucus and never got to the cells.
To optimize efficacy.
Yeah, essentially, yes. The more material you can get to the cells, the more that you can actually get taken up by the cells. If it's stuck before it even gets to the cells, you've got a problem.
When you're in your research, you have this, you have found this drug, but how do you commercialize it? What's it's, I guess, hard for a researcher to do that.
Of course, and we couldn't do this on our own. We work very, very closely with our technology transfer office, who have the experience and the knowledge and the expertise to help us put together a package that is attractive. So we have to have all our IP in order, we have the right patent protection. We are able then to negotiate with, for example, potential licensees, and that's something we've done in the GBOC project. When we first started looking at modifying mucus, then we were looking at modifying the properties of mucus to improve mucus clearance from the lungs in lung diseases. And GBLOX for symptom relief in respiratory diseases is out-licensed, has completed phase 2A clinical trials, so successfully.
So you're clear on toxicology as well?
Yeah, the tox looks good. We have a situation where, because we've come so far in respiratory diseases, then tox for an inhaled treatment is well defined and very safe. If you're looking at oral delivery, then GBLOX is an alginate product. Now, alginate is there in the European Pharmacopoeia, generally regarded as safe. Alginate is used as a food ingredient. Ice cream, tomato ketchup. So you've eaten alginate.
Right.
So we're safe there. And one of the questions we're often asked is, but just a second, you've got this protective secretion and you're telling me you're opening it up. You're making a hole in it so things can get through. Isn't that dangerous?
Yeah, that was sort of my idea.
Yeah.
But
well, actually, here the body works for us because you have a continual secretion of mucus. And healthy humans, such as yourself, secrete 10 litres of mucus a day from your various mucosal surfaces.
So we are talking about short window.
Yeah, absolutely. We modify the mucus that's there at that time. And then
When
new
you
mucus
eat
is
your-
secreted. And we're very careful here with using the GBLOX. We're only opening up. We're not destroying the mucus. And that's very, very important because the mucus is there for a reason physiologically. And if you remove the mucus, if you destroy the mucus, then your body's natural response is A, to wash away whatever's causing this problem, and B, produce more mucus
Right.
to cover this surface. So it's very important that we don't stimulate more mucus production. That wouldn't help.
And in the future, how does that look?
Well, as I say, we work very closely with our technology transfer office, and we are very aware of the other challenges that exist. And we are now just starting a project where we are looking at GBLOX in drug delivery still, but rather than at mucosal surfaces, we're actually looking at intravenous delivery of GBLOX. And this is very early stages in this project, but the toxicology looks good in mice, so it's promising at this stage.
Well, thank you a lot, Catherine, for letting me know a little bit more about your research. Thanks a lot.
You're very welcome.